Hey everyone, today we want to go ahead and look at finding the distance between two skew lines. And the lines I have are given up here. So I have kind of the x1, y1, z1 is line 1, which is 5 plus 4t, 3 minus 7t, and 1 plus 2t. And then line 2, the x, y, z are the 4 minus 2s, negative 8 plus 6s, and 2 plus 3s. So these are the two lines. The one has parameter t, one has parameter s, and we just want to find the distance between those two. You should have seen another video how to tell if they're skew, parallel, or intersecting. In this one, we're just going to graph them. It'll be pretty obvious that they're skew. What we're going to do is go ahead and graph each line, and I have this kind of broken down into folders that we'll go through. So looking at line 1, line 2, the main idea of how we're going to find our distance, some final computations, and then the final actual distance, and kind of visualizing the vector that is involved there. And then kind of this last folder is a few more visualization things you can do to kind of make sense of what we're doing. So to start off, I'm just going to click this folder here. This will show line 1. If you want to see some of the stuff involved, you just click the arrow and it'll show it. And then if you don't want to see it later, you can hide it again. So right now I have sort of the parametric form, right, of this line. So the 5 plus 4t, 3 minus 7t, 1 plus 2t. Right now I have t going between negative 10 and 10, which is good enough for us. And I also have a point p, which is the point we know that's on the line, the 5, 3, 1. So that's the beginning coordinate there, the 5, the 3, the 1. And then v is going to be a vector starting at p. So since I've defined it, I can just use that value of p, and then p plus the vector values. So the 4, negative 7, and 2 is what I'm adding. So I'm starting at p, ending at p plus that vector amount, which shows me that vector v. So you can see that is right here with the kind of endpoint there. That's my dot, and then the arrow pointing, in this case, to the left, kind of toward, right, this negative y direction that's right there. So that's what I'm looking at right there. There's a couple other ways you could graph this line that I'll mention just as a side note. So you could also take p plus this vector direction, right, the 4, negative 7, 2 times t. This would also graph that same line, right? So this is the same line. Gives you basically the same visualization there, just another way to write it, right? So this would be what we call the vector form of a line. This is the first one was the parametric form of a line. You could also do the symmetric form of a line. So this last one, again, that blue is kind of right on top of the gray and the purple as well. So this is the symmetric form. The x, basically you just solve for t, right, on all these, and you get, in this case, the 5 plus 4t is x, and then solve for t. So I subtract the 5, divide by 4. This is my x. Or sorry, my t, which is x minus 5 over 4. Do the same thing, solve for t on the second one and the third one, and I get these fractions for my y and my z. And since they're all equal to t, they're all equal to each other, and you set them equal to each other. So that is another way that you could type it in Desmos if you want to see that line. So it'll accept any of those sort of parametric form. There's the vector form, right? P plus those vector values times t, and then the symmetric form, which is right there. So I'm going to go ahead and hide this one. So we're just looking at that purple line for line 1. We can do the same thing for line 2, right? So if you want to see those, I didn't do all three forms in this one, just the one. But we have that parametric form of the line, the point Q, which I know is on my line. Excuse me. And then the vector, which I'm calling W, which is starting at that point Q and heading out sort of as defining the direction of that line. So there's that one. So these 2 points right here, right, are sort of sitting here in space, and I might actually add, if you want, you can, for some of these guys, I don't know if it'll let me add a label or not. It's not looking like it will, so I'll just leave those as it is. Um, so we got Q in line 2, P in line 1. So we'll just remember P is purple for that line 1. So you can tell, right, these don't intersect if you look from a certain perspective, right? These are kind of, looks like parallel if I'm looking from this weird angle right here. Um, from any other direction, it might look like they intersect, right? But in 3D, they actually don't, right? So there's a certain perspective you can look at where these two lines will look kind of parallel. And what is happening is they're part of two parallel planes, right? So there's two separate parallel planes here that they're part of, but they never actually meet and touch. So they'll always be, kind of separated by that gap that's right there. So this is what we call skew lines. And there is a shortest distance in between those, which is this distance if I'm looking kind of um, along that perspective where these are parallel. That is the shortest distance between these guys. Um, any other point, right, to any other point is going to be longer than that. But there's one certain distance where these two gonna are perpendicular to each other, or I should say perpendicular to another line that intersects both of these, and we're just looking for that short distance that's right there. So here's our main idea that we're going to work on is the shortest distance, like I said, it's perpendicular to both lines, and we actually do have a way to find that. Right? So we can find a vector that's orthogonal to both of the lines just using the normal vector. So we're going to do a cross product, right? Cross product V cross W. So remember, V is going to be this purple vector, W is going to be that red vector. We're going to cross them. And what's going to happen is I'm going to get this gray vector right here pointing normal to both of those. Now, the way Desmos displays this is starting with whatever starting point you had on V, right? So your first vector, whatever starting point that was, that's where it'll start. Vectors can start at any point. So there's probably actually some other point down here where this will look a little bit better, but this is the direction that my normal vector is heading in, right? So both of these lines are going to be perpendicular to that. What I can do after that, right, is go ahead and take a look at a few things. So one is this vector from P to Q. So I'm going to go ahead and draw that in. All right, so there's my vector from P to Q. And what I'm going to do is I'm going to project that vector. So I'm going to zoom in a little bit so you can see this better. I'm going to project that vector onto this normal vector. So if I'm kind of at the perspective where these two are parallel, uh, then that vector project onto my normal vector, and that length of the projection, will be that distance between those two lines. So the notation, right, in Desmos can get a little bit weird. You're not allowed to write multiple letters, but you can use subscripts, which can be as long as you want. So right now I have this P sub Q as kind of my PQ vector between those 2 points. I have the projection of PQ onto N, kind of written this weird way with that very long subscript, but uh, that's just a way of notating it for me so I know what I'm talking about. So this is the projection of that orange vector PQ, right, onto this gray vector N, that normal vector. And to do a vector projection, right, you can just do PQ.N over N.N and then multiply that by the actual vector of N. So this first fraction is a scaling factor, right, and then you're going in the direction of N. So that gives me my vector projection right there. Really, though, we want the length of that, not the actual vector itself. So you can compute the length, right, by doing what they call the scalar projection of PQ onto N. So this is the PQ dot N, right? But then just divided by the magnitude of it. So what this ends up being is if I times this by the normal vector, right, N over magnitude of N, then I get this exact, the exact thing up here, the projection of PQ on N as a vector. This is just the scalar, like the length of that guy. So we'll just do that computation PQ dot N and then divided by the magnitude of N. That gives us this 5.761, etc. That's right there. So that would be my kind of final answer for this one. This is the distance between those lines, right? A couple other things to note on this, right, is so I'm going to go ahead and show this. This is the same vector, right? So this blue and this green are exactly the same. I'm going to go ahead but I've created a slider where I can slide this one around, right? So I can kind of slide this vector around on that line. So what's going on is, right, if I look at a different kind of perspective here, um, there's all kinds of points like this, P and Q, right, where that distance is pretty far. But if I go ahead and slide this normal vector, right, to some point right here, all right, this is going to be kind of my shortest distance right between those. This is the distance where this forms an orthogonal right angle between that normal vector and the red line, also forms that right angle between the normal vector and the purple line, and that will be where that shortest point happens, right? So where that shortest distance occurs. So looking from a certain perspective, right, it can be, kind of anywhere that you want it when they're looking parallel, but really there's one specific place in space where that's happening, and that's kind of right there. In terms of how I got that blue vector to slide, in case you're curious, I'm just defining a point as kind of that starting point P, right, which is the 5, 3, 1, and then I'm adding this vector multiplication of 4, -7, and 2 times m, right? So 4m, -7m, 2m times those x, y, and z values. We're just adding those together, and that will, depending on the value of m, right, if m is 0, that'll put me exactly at P, all right, kind of right here. And then as I change m, that'll add a scaling factor of that vector, right? So if m is 1, I'm exactly at the end of that vector. And if m is bigger, I go further. If m is negative, I go backward. So that allows me to just kind of slide this around in there. So again, there's kind of that one specific place, right, where we get kind of that shortest distance between those two lines that are right there. A couple other things to note, right, on this is that the vector, so that's the actual point, right, being able to slide it, that first thing. The vector arrow, right, this is kind of a weird thing to think about. But I'm taking a vector from that P1 to P1, right? It's basically a zero length vector, but starting at P1 and ending at P1. So this kind of fools Desmos into saying, I want to start at P1, right? So Desmos always takes the first vector, whatever it is, chooses that initial point as your starting point. So this kind of fools it into thinking, oh, here's where I want to start. It's at that P1. So I'm starting at P1 and then just, drawing a zero vector to the same place. But that tells Desmos, here's where I want to start. And then I'm adding, right, this D, so that was my distance, right, distance between the lines, times a unit vector in that normal direction. So the length of this unit vector is 1, and then I'm multiplying it, scaling it by D. So this gives me my n, right, my normal vector, that gives me my direction. The magnitude of n, then I divide it by unitizes it, so it's length 1, and then we'll scale it by that d, right, which makes it exactly as long as I want. So, so that vector there will just be, right, exactly that same length, down here as the distance that we already found from before, right? So that was my answer. It just wasn't kind of in the right spot. So now we can move it and get it sort of over there in the right spot to look at it. A couple other things to note. So I'm going to go ahead and use this last little section here. Is that we have two planes, right? So these two planes, if let me just make sure, yeah, I have translucent surfaces turned on. If you don't, right, it'll just look like that. But now we can see at least a little bit through them. So these are two planes, right? I mentioned this before. Two planes that these lines are on, and those planes happen to be parallel, right? They both are given by this normal vector, right, for those kind of ABC components that are right there, and then equal some number, right, which is giving me the exact position of where that line is. So you get like the AX plus BY plus CZ equals D type of equation for those. But this is kind of what's going on with there is we got two planes. So the actual distance between those planes is the same as the distance between the lines. So this is pretty equivalent to finding distance from a point to a plane as between two skew vectors. A lot of these, if you just kind of think about the geometry underlying what's going on, a lot of these computations, even though it might look different on the surface, what they're asking you to do, find distance between two skew lines versus find the distance between two planes or the distance between a point and a plane, they're all basically the same computation. They're all just going to default to this kind of PQ dot N type of scalar projection of PQ on N, that sort of thing. So just a few things to think about as you're solving some of these equations in the homework. Uh, Definitely practice writing some of those out by hand, but also, um, you know, try using another tool like Desmos or, there's lots of other tools out there like Mathematica, MATLAB, Maple. Usually those you have to pay for. Desmos is free. Um, so it's just one tool that you can try to use as you're working through to see, right, what does this look like visually? What sort of components would I want to draw in to be able to solve these types of problems? Hope that was helpful. And if you got any questions and you're in my class, let me know. If you're just finding this on YouTube, hope you enjoyed it. And we'll see you next time.